Welcome back. Alright, now it's time to start taking our idea that, okay, we know that it's a tricky idea as to whether the flow is going to go over obstacles like hills and stuff, or is it going to go around them, or is it going to get backed up behind them. Let's just work out with the situations where the flow is going to be following the terrain. We're talking fruit numbers in the vicinity of 1 or something like that. And so, let's picture this, some kind of obstacle near the surface. Now, what I'm trying to illustrate there is like a hill or something like that. And I just for now drew it in kind of a Dr. Seuss-looking pointy hill. It doesn't really matter how you draw it. But we're saying that we have flow that will approach from the windward side of the obstacle, the side from which the wind is coming. And we're going to say this flow just gladly goes up and down over the hill, following the terrain, onto the leeward side of the mountain, and then moves away. We're just following the terrain. At the surface, that's not terribly hard to picture. I don't really have that much trouble picturing how an air parcel would follow the terrain and go up. But what about, like, if I followed a streamline higher up? I mean, like that top streamline that I have drawn here. Do I really buy that that's what the flow is going to be doing? Why would that air parcel have decided to respond so dramatically to a hill that's quite far below it? Is that what would really happen? Well, the answer is no. Actually, the higher up you get away from the surface itself, the ability of that orography to influence the flow gets smaller and smaller. Like I showed you here on this top streamline here, once you are significantly higher than the top of the hill or the mountain or whatever, the ability of that mountain to influence the flow is not all that great. Now, farther down in this lecture, we're actually going to figure out how high up we're talking about here. How high are we going to go above the top of the hill or mountain or bluff or whatever before the mountain is no longer affecting the flow? But I think we can agree that the flow near the surface is going to make a huge change to its flow as it goes over the flow, closely following the terrain, or the orography, if you will. Whereas at some height above the ground, it will be far enough up that there's little to any change to the flow due to the underlying terrain. Again, keeping in mind, we're not necessarily talking about the Alps here, okay, or the Himalayas or something. This could be, I drew it as some big pointy mountain, but this could be a hill in Nebraska, okay, or a hill in western Iowa. Alright, so we have this idea, though, that there's going to be some change in the amount to which the flow is being perturbed by the underlying orography as we go higher and higher up in the atmosphere. This is actually a really subtle and interesting point, because this is going to have a big effect on the wind speed that we can fairly easily quantify. Okay, I've tried to draw there with that parallelogram. I'm trying to draw like a plane that is normal to the flow or perpendicular to the flow, and the flow is moving through. There's a flux of mass of air through that box that I drew right there. Where upwind, on the windward side of the orography, the flow is going through a certain amount of space. There's a plane there that the flow is going through. And what I want to show you here is all that same amount of flow, that same amount of mass is going to have to get squeezed through a narrower area at the top of the hill, because we know that all that mass is going to have to pass through that smaller area at the top. Okay? It has to squeeze through that smaller plane up at the top of the mountain there. The flow is going to have to speed up to do that. The same amount of mass that was passing through that larger plane upwind of the orography now has to pass through a smaller plane, so the way that will happen is for the rate at which the flow is moving to accelerate. Now, your book is making a peculiar choice here. Your book is calling this equation that describes that Bernoullis Equation. And we're going to get off on a little bit of a tangent here about that whole business of Bernoullis Equation. But I want you to be aware here, that's what your book is saying. Your book is saying that there's actually a nifty little relationship here between the wind upwind of the mountain and at the top of the mountain, or hill, or mesa, or whatever. And it gives you this lovely little equation where the wind speed upwind of the orography, U1, is related to the wind speed at the top of the orography, U2, by this equation here, where the A's these are the areas of those two planes that the air is going through. The area of the wind, the area that the air is passing through upwind is, related to the area of that the wind is pushing downward. Now, we haven't yet figured out what those areas would be. How much is this flow going to have to be restricted as it goes over the terrain and so on. But as a broad idea, I can see how this would work. And as we get that area to be smaller, as we get the flow to squeeze over the top of the mountain, clearly the wind speed U2 will have to increase. And this makes a measure of sense except for one thing. Good old Daniel Bernoulli, a Swiss mathematician who lived in the 18th century, would say, "Pardon me, but I disagree. That is not my equation." I have literally no idea why your textbook is calling this Bernoullis Equation, because this is wholeheartedly not Bernoullis Equation. It is actually very, very much not Bernoullis Equation. In fact, it is something that is sometimes in meteorology referred to as the gap wind equation, and you'll see why it's called a gap wind equation in just a little bit. I have absolutely no idea why your book is calling this the Bernoullis Equation. It could be that Bernoulli also developed this equation, but this is wholeheartedly not Bernoullis Equation. I don't know why that is. So let's talk about this idea, though. Let's keep using that equation, that A1U1 equals A2U2, which is the gap wind equation, and kind of picture what's going on here. I mean, like for example, I have a garden hose down there, and there's a fat stretch of the hose, and then I put like a kink in the hose right there. And so where the hose is wide, the water is flowing through the hose, and it moves relatively slowly. Whereas as the flow gets constricted to move through that narrow kink in the hose, the water is going to have to move relatively fast to move the same amount of water through that narrow place as it is moving through the wide place. This is how like a nozzle works on your hose. Okay, it creates a narrow little gap inside the nozzle for the water to pass through. The water has to accelerate to move through that little gap, and that causes the water to move much faster than it is moving in the hose, and you can spray the water a long distance. We're going to just real quick use the subscript D to mean the narrow part and S to mean the wide part, just because that's the notation that was used in another book. But you can see how you just end up with the same equation here. Instead of A1U1 equals A2U2, now it's just ADUD equals ASUS. And it works just fine. Now, a gap doesn't have to be just like in a hose or something like that, like these analogies that we're talking about here. A gap could be like an area, like a pass between two mountains, where slow flow approaching that gap has to be constricted by the orography to go through that narrow little gap. And in fact, this can be a big part of the story about like winds in valleys and so on, between two obstacles to the flow, like two large mountains or something like that. But in meteorology, we love gap winds, because there are some brilliant examples of places on Earth where they get these amazing gap winds, where the winds get accelerated as the flow moves through a narrow gap between two obstacles to the flow. And I want to show you one of the coolest ones here. There's a phenomenon in meteorology called a Tehuantepecer. A Tehuantepecer is a particular type of wind that happens over a part of Mexico, well, a part of the Pacific Ocean adjacent to Mexico, called the Gulf of Tehuantepec. You probably see that on this map here. This is a chunk of Central America here on this map here. You've got the Gulf of Mexico to the north, and the Caribbean to the east, and parts of the Pacific to the south, including the Gulf of Tehuantepec. Tehuantepecers are winds that happen over the Gulf of Tehuantepec. And the coloring on this map is showing the orography, the elevation of the ground. And you'll be forgiven for not being familiar with the orography of this region here, but in general, to the west, you have this very high range of mountains called the Sierra Madre. Okay. Farther down into Central America, you have another section of mountains that are also called the Sierra Madre. They have slightly different parts to their name there. But in between, right through that isthmus of Tehuantepec there is a narrow pass between these two mountain ranges. It's called Chivela Pass. Chivela Pass is quite low and quite narrow. And it is a very promising place if you want to get between, say, the Gulf of Mexico and the Pacific Ocean. In fact, back before the Panama Canal was built, this was a, like there were railroads and stuff like that that was carrying the contents of ships across the Chavela Pass. It's low, it's relatively narrow, it's a nice little pass for getting from the Gulf of Mexico to the to the Pacific before there was a Panama Canal. So you have this wall of mountains to one side, and you have this wall of mountains to the other side, and this relatively narrow pass between the two of them, a brilliant case study of an example of a place where you can do gap winds. Anytime there's relatively weak flow over that Gulf of Mexico, and it's being forced to go squeeze through that relatively narrow gap there through Chavela Pass, you're going to get an amazing phenomenon well described by the gap wind equation. Now, it depends entirely on the stability, or another way to say it is the Froude number. A lot of times the flow will just go happily over the mountains and we don't get this. But if the air is relatively stable and it can't get over the Sierra Madre Mountains, it'll have to squeeze through that narrow Chavela Pass. And you'll get a rip-roaring wind coming through that Chavela Pass there. So, like, for example, on this particular day here, I don't remember, I think these are miles per hour, but on that particular day, as the winds were coming off over the Gulf of Mexico, these are actually for satellite-derived winds, so it's a remote sensing type of wind here, but a relatively weak, I mean, it was still actually pretty brisk, maybe 20-mile-an-hour winds or something over the Gulf of Mexico, were being forced through Chavela Pass. The gap wind equation said that the wind would accelerate, and you can see we had winds of on that particular day of 45 to 50 miles per hour out over the Gulf of Tehuantepec. This violent windstorm is called a Tehuantepecer. It is part of the pattern of certain local winds. The pattern in meteorology is you attach ER to the region where they're happening. Okay, it's just a notation issue in meteorology. Don't worry about that. So a strange wind that happens over the Gulf of Tehuantepec is a Tehuantepecer. Okay, here's another one. Now this actually happens to be wave height rather than winds, but what's causing the waves is the winds. And again, on this particular day, you can see there's this huge waves. They're in feet. They're having 12-foot waves off the Gulf of Tehuantepec there, and it's being caused by winds just shooting through that very narrow gap in Chavela Pass. This is a nice example. There are actually other places in the world where in fact, there is actually 2 or 3 other places in Central America where we have gaps in the mountain ranges. This just happens to be one that I was involved in some research studies over the years and happened to have good links about and so on. Again, here's another example of it. On this particular day, they had wind speeds of 15 to 16 meters per second. That's 35 miles an hour off of the Gulf of Tehuantepec because there was a Tehuantepecer happening. Air was being forced because of low Froude number to squeeze through the Chavela Pass instead of going over the Sierra Madres, and they got these huge gap winds. Tehuantepecers and other gap winds are important for lots of interesting reasons. Personally, I think one of the coolest things about them is that they stir up the oceans. And when they stir up the oceans, as it happens in the eastern Pacific, where the Tehuantepecers happen, the water near the surface tends to be kind of nutrient deprived. Phytoplankton and stuff use up the nutrition quickly, and then there's not much life going on at the surface. But when there is a Tehuantepecer happening over the eastern Pacific, what happens is the very strong waves mix the ocean really well, and cold, nutrient-rich water from down below the surface, below the layers where sunlight penetrates, this cold, nutrient-rich water gets mixed up towards the surface. Another example of how mixing kind of makes things more uniform. Instead of there being a gradient between there being nutrient-deprived and nutrient-rich water, now the nutrient-rich water is mixed towards the surface. The sun shines on it, the phytoplankton go nuts, and you get these phytoplankton blooms that can actually be seen from space, okay? This is imagery from an ocean color satellite that monitors the health of oceans and so on, and you can see this big phytoplankton bloom happening over the Gulf of Tehuantepec. You can actually see there's other ones happening at other gaps in the mountains along the coast of South America. And in fact, this is a big deal because that phytoplankton then activates the food chain little fish eat the phytoplankton, bigger fish eat the little fish, and so on. That's actually, the Gulf of Tehuantepec is a big area for fishing things like tuna and so on. And it's only able to sustain the life of giant fish like tuna. In case you didn't know, tuna are huge. Because of this active food chain that is kept going in a relatively nutrient-poor area by the occasional Tehuantepecker. It's actually very interesting how this works. Some Tehuantepeckers are astonishingly violent, and I'm going to show my age here by talking about a particularly interesting example of one. Now, on March 13th, 1993, we had this enormous storm happening in the United States, known as the Storm of the Century. The Storm of the Century was an enormous mid-latitude cyclone over the United States. One of the strongest ones ever observed. It had pressures of like 940 millibars. You know what else has a pressure of like 940 millibars? A hurricane. It created huge storm surges. It was, you wouldn't remember because you're way too young, but it was the storm that destroyed President George Bush's summer White House in Kennebunkport, Maine. I dumped 40-some inches of snow in northern Georgia. It was a huge, huge storm. And I have a satellite image of the storm of the century down in the inset here. And you can see this giant cyclone moving up the east coast of the United States. And a big, cold air mass from Canada is plunging south across the United States, plunging south across the Gulf of Mexico, almost all the way into the Caribbean and so on. We have this cold, dense air from Canada pushing across places like Cuba. Okay, weird, weird storm. And if you zoom in a little bit on this guy, let me see if I can do that right here. If I zoom in on that area with the rectangle right there, you can see how that cold, dense air is plowing across the Gulf of Mexico and then hitting the Sierra Madre Mountains in Mexico and in Central America, and being forced to rise up the mountain. You can actually see the clouds there as clouds form as the air is being forced to rise up the mountains. But the flow is in general not getting over those Sierra Madre Mountains because it's relatively dense at the surface, it's relatively stable. Those cold, dense air parcels at the surface are just not going to get lifted over the Sierra Madre. Low Froude number situation. We have relatively stable situation. The flow is not going to be able to make it over the mountains. It's going to find a gap. And it finds, in fact, Chavela Pass. And air comes rushing through Chavela Pass. I don't remember what the exact wind speeds measured in Chavela Pass at that time were, but it's like 60, 70 miles an hour. Okay? Air was just racing through Chavela Pass. In fact, something interesting happened. Air raced through Chavela Pass and squirts out over the surface of the Gulf of Tehuantepec, as it tends to happen. And you get these winds rushing out over the ocean and so on. And you see that little arc of clouds that is formed, kind of a C-shaped area of clouds out ahead of the Gulf of Tehuantepec? That's the leading edge of this air racing forward over the Gulf of Tehuantepec. Those winds were so strong, hurricane-strength winds, they were picking up sand off the beaches in western Mexico, after squirting through Chavela Pass as a gap wind, picking up that sand, carrying that sand out to sea, and sandblasting the sides of ships that were facing towards the land. These like shipping vessels and these cruise ships and stuff like that were out there got completely sandblasted on their side that was facing the land. It is a very cool storm. Don't get me wrong, the Storm of the Century is actually a hugely interesting and important storm for lots of important reasons. This is just kind of one of the little nifty things that happened associated with this storm. Okay. We said we agreed. This equation here, this is not Bernoullis equation. You might have heard about Bernoullis equation in lots of other contexts and so on. You might have, a high school science teacher might have told you Bernoullis equation is why airplanes fly. Bernoullis equation is part of the story of how hard drives work on your computer. If this thing isn't Bernoullis equation, what is Bernoullis equation? We'll come back to that in just a little bit. But let's actually talk about this gap wind equation for just a couple of quick questions here. Question 3. The gap wind equation suggests that winds should be blank at the top of hills. Should they be stronger, weaker, zero, or negative? What's the gap wind? Now, I'm not saying necessarily what they are. I'm saying what does the gap wind equation tell us should be happening at the top of hills? Not necessarily mountains or mountain passes or anything like that, just a hill. All right, make a choice from those 4 options and get a little feedback before you move on to question 4.